In this lecture, we will discuss the sun, the earth, and the moon as a system, how the three bodies interact. We're not yet going to discuss the objects themselves, but we will get into that in the coming weeks. We're first going to look at the three major motions that affect Earth. The first and third ones you're probably very familiar with, but we'll go through the important bits about all three in this lecture. The Earth rotates on its axis. This rotation takes 24 hours and causes the day-night cycle. Earth also revolves around the sun. This revolution takes 365.25 days and is the length of 1 year. We ordinarily think of the year as only 365 days. This extra quarter of a day is why we have leap year every 4 years. It doesn't take exactly 365 days for Earth to go around the sun. It takes about 6 hours longer. But added up over 4 years, we get 1 extra day. This image actually shows two things we're looking at in today's lecture. Number one, as Earth rotates, it moves from west to east, counterclockwise if you're looking down from above the North Pole. This brings the east coast into view of the sun before the west coast, which is why the eastern time zone is ahead of central and western time zones. Also, number two, the tilt of the Earth causes the seasons. In this photo, if the sun is off to the right, the northern hemisphere is having summer as it's tilted toward the sun. The southern hemisphere is having winter as it's tilted away from the sun. But we'll get into seasons more later in this lecture. Remember, the ecliptic is the path that the sun and other planets seem to follow around the Earth. The plane of the ecliptic is a flattish disk around the sun where all the major planets of the solar system orbit. Notice in the smaller picture, it shows the plane of the ecliptic as compared to the plane of the equator. Notice that the Earth is tilted at 23.5 degrees. This number is important. As I discussed in the last lecture, stars always rise in the east and set in the west, since Earth rotates from west to east counterclockwise. The stars near Polaris seem to trace a circle around Polaris, never quite setting. In Pensacola, Polaris sits 30 degrees above the horizon because we are located on latitude 30 degrees north. This is a more complete image of star trails taken over the course of an entire night, or at least several hours. Due to Earth's tilt, the sun's path across the sky varies over the course of the year. You can actually calculate just how high the sun will be in the sky. The example shown is for someone at 40 degrees of latitude, so farther north on the planet than Pensacola sits. New York City is at about 40 degrees north latitude. The formula is simple. Take the number 90, subtract your latitude, and add 23.5 degrees for summer. For us in Pensacola, 90 minus 30 is 60, then plus 23.5 would be 83.5 degrees in the summer. So the sun is not 90 degrees up directly overhead, but it's pretty close. In the winter, the first step is the same, 90 degrees minus our 30 degrees latitude, then subtracting the 23.5 degrees of tilt gives us only 36.5 degrees. Notice in New York in the winter, it's even smaller. The sun spends a much shorter amount of time during the day above the horizon, which is part of the reason why winter is colder than summer. The tilt affects not only how high the sun is in the sky. What else would be different if the Earth was not tilted on its axis? I actually already mentioned it. The correct answer is that there would be no seasons. If Earth were not tilted, the climate would be the same all year around. We'll look at why in a bit. Another important thing to know about Earth's tilt is that the direction of the tilt changes slightly. Imagine a child's spinning top. It spins very tightly and remains very stable as long as it's moving rapidly. But as it slows down, the top starts to wobble. This is what's happening to the Earth. Its axis traces a circle in the sky, and the North Star actually changes over time. It was Thuban 3,000 years ago, it's Polaris now, and it will be Vega in another 12,000 years. This wobble is called precession. The amount of tilt is still the same 23.5 degrees, but the direction that the angle is pointing changes. The reason for this wobble is that Earth is not a perfect sphere. As it rotates, the planet is actually squashed a bit, making it wider side to side than it is up and down. Look at the image. Earth is only slightly deformed. The difference between the two radii is only about 20 kilometers. But compare that to Jupiter. Jupiter is much more flattened, and its equatorial radius is over 4,000 kilometers longer than the polar radius. The reason for this deformation is that it's caused by the planet's rotation. Jupiter is much more deformed because it's made of gas and spins much more rapidly than Earth. But as the sun and moon pull on the Earth, this causes Earth's precession. This change is very slow, about a degree every 72 years. So for your entire life and many more generations, Polaris will still be the North Star. But this slow movement does add up over time. The complete cycle takes about 26,000 years. So even though the current pole star Polaris will lose its status when Vega or another star takes over, it will regain it again in 26,000 years and be the North Star again. So that's all for rotation and precession. Let's move on to revolution. Again, I mentioned earlier that revolution takes about 365.25 days, but you'll notice that even that number is rounded. So every once in a while, we actually have to throw in not only a leap year, but even sometimes a leap second has to be taken off in order to keep everything lined up properly. Earth does not revolve around the sun in a perfect circular orbit. It follows an elliptical or egg-shaped path. Notice this word is really similar to the word ecliptic that I've used in the other lectures we've covered so far, but it's not the same word. You have to be super careful as there are several words in this unit that are really similar. In the picture, you can see that the sun is not in the center of the ellipse, but is situated at one of the foci. Notice that the center of the ellipse is not marked. You can draw a circle from one center point if you know the radius, but to construct an ellipse, you need 2 points, each called a focus, and the plural of focus is foci. Eccentricity is a measure of how much an orbit deviates from circular. You've probably heard the word before, probably talking about people, not orbits. If you have an eccentric neighbor, that means they're a little different. Same thing with planetary orbits. The eccentricity value is a measure of how different an orbit is from a perfect circle. A planet with an almost circular orbit has a low eccentricity, while an object with a much more oval-shaped orbit is said to have high eccentricity. The closer a planet is to the sun, the faster it moves. Mercury is closest to the sun and revolves much faster than the Earth in only 88 days. Not only is its orbital path smaller, it's actually traveling at a faster rate of speed. A planet like Saturn, which is much farther away, takes much longer to revolve around the sun. Because of this elliptical orbit, sometimes the Earth is closer to the sun than others. These two vocabulary words are really important. Perihelion, para means close, helio means the sun, is the point in the orbit where a planet is closest to the sun. And the planet actually travels faster at this point in its orbit. For Earth, this occurs on about January 3rd. Aphelion is the opposite, when the Earth is farthest away from the sun and is actually traveling more slowly. This happens on about July 4th. This may sound backwards to you, but we're actually farthest away from the sun in the middle of summer on July 4th, and we are closest to the sun in the winter on July 3rd. So it isn't distance from the sun that causes seasons. Do you remember what causes it? Don't forget, it's the tilt of the Earth that causes seasons. In this image, the northern hemisphere is having winter, while the southern hemisphere is having summer. Notice the angle of the sun's rays. In the north, they're hitting at a very low angle, but in the south, they're hitting the surface much more directly. Since the northern hemisphere is tilted away, it's having winter, while the southern hemisphere is having summer. You can picture it maybe more easily like this. Imagine you're shining a flashlight on this globe. At position A, you're holding the flashlight straight, so all the light is focused on that one area. This would be summer. But at position B, you're holding your light at an angle, so the same amount of light is spread over a greater area. That would be winter. The amount of heat and light radiation leaving the sun and arriving at Earth doesn't change, but how it is concentrated does change over the course of the year. Here in the top two pictures, you can see the difference between summer and winter. The left picture has the north pointing toward the sun, while the right has the north pointing away from the sun. The bottom picture is showing fall or spring. The picture is a bit misleading though, since it looks like the Earth is not tilted at all. The Earth is always tilted at the same 23.5 degrees, but at fall and spring, the Earth is just tilted to the side, not toward or away from the sun. If you look carefully, you can tell they're still trying to show you that the Earth is tilted in that bottom image by showing the whole Arctic Circle at the North Pole and none of the Antarctic Circle in the south. The picture shows the Earth tilting out of the screen towards you. So here we can see the whole process a little more completely. For the northern hemisphere, we have summer here, tilted toward the sun, fall here, tilted toward the side, winter here, tilted away from the sun, and spring here, again tilted toward the side. For the southern hemisphere, the seasons are always opposite of what's happening in the north. Note also that the first days of summer and winter are called solstices, while the first days of spring and fall are called equinoxes. Equinox literally means equal night. The vernal equinox is the first day of spring, and the autumnal equinox is the first day of fall. Remember, Earth is tilted, but to the side, neither toward or away from the sun, so every place on Earth gets exactly 12 hours of daylight and 12 hours of darkness on the equinoxes. The sun lies directly over the equator. Equinox, equator, and equal day and night. This image does not show that Earth is tilted, though it should. On the summer solstice, when the northern hemisphere is tilted toward the sun, the north actually gets more hours of light. Look at the line labeled Tropic of Cancer. This line is at 23.5 degrees north. It gets the most direct solar rays today because of Earth's 23.5 degree tilt. Can you see that more than half of that line lies within the daylight side and only a small part of it lies in darkness? The farther north you go, the more hours of light you have. Polar bears living north of the Arctic Circle would have 24 hours of light at this time of year. But at the opposite time of year, in December, the northern hemisphere is tilted away from the sun. The sun lies directly over the Tropic of Capricorn at 23.5 degrees south. As the southern hemisphere has summer, much more of the northern hemisphere is in darkness, and that's why the winter is colder. In fact, no light hits the areas north of the Arctic Circle at all. You may notice that these two lines, the Tropic of Cancer and the Tropic of Capricorn, often labeled on a globe, have names associated with the couple of zodiac constellations. That's not a coincidence. If you're in my lab class, we'll look at why those lines are named the way they are. This is why the length of a day changes over the course of a year. Have you ever noticed that in the summer, it gets light out really early in the morning, but it also stays light well into the night? Whereas in the winter, the sun comes up later and sets earlier? A day is always 24 hours, but the number of hours of daylight changes. In Pensacola, we get about 14 hours of light during the summer and only 10 hours of darkness. It's reversed in winter. At the spring and fall equinoxes, we get exactly 12 hours of day and 12 hours of darkness. The equator always gets 12 and 12. Those are the movements of the Earth you need to understand. Now, let's move on to movements of the moon. The moon rotates and revolves just like the Earth does. It takes the moon 27 days to rotate on its axis and almost the exact same amount of time to revolve, which is why we never see the backside of the moon. The entire lunar cycle, though, lasts 29.5 days, slightly longer, because even though it takes the moon 27 days to get around the Earth, remember that the Earth has moved along its orbit as well, and it takes the moon a couple extra days to catch up. You don't need to memorize these exact numbers, but notice that each one of them is about a month. In fact, the word month used to be spelled M-O-O-N-T-H. The whole cycle of the moon takes about a month. The moon rises 50 minutes later each day, and the tides are later each day by the same amount because it has to catch up with Earth's rotation. The moon, like the Earth, revolves in an elliptical orbit, meaning that sometimes it's closer to the Earth than others. At perigee, the moon is closest to the Earth and looks slightly bigger. And at apogee, the moon is farther away and looks slightly smaller. Have you ever seen online when the news says there's going to be a supermoon? The moon isn't really particularly any more super than normal, but it does look a tiny bit bigger just because it's at the point in its orbit where it's slightly closer to the Earth. Notice that these two words are similar to the words perihelion and aphelion we talked about earlier. The prefixes peri and ap still mean close and farther away, but the suffix G refers to the Earth. Remember that geology is the study of Earth. Due to the fact that the moon does not make its own light and is just reflecting sunlight, the position of the moon and the sun compared to the Earth allows us to see different portions of the moon's surface illuminated at different times. These different shapes we see are called phases. It's important to note that even when we see only a tiny bit of the moon's surface illuminated, half the moon is always reflecting light. It's just that the rest of the lit portion is on the back side of the moon that's facing away from Earth. Remember, the whole cycle lasts about a month. This calendar shows the year 2014, which isn't special for any reason, but I chose this month because the new moon occurred on the 1st. Look at January 1. This is the new moon. The side of the moon in darkness is facing toward the Earth. For the first 7 days, the moon is in a waxing crescent phase. Waxing means the amount of light is increasing each day, and the crescent is what we call that skinny banana shape. January 8th is showing us the first quarter moon. It looks like a half, but we call it a quarter moon because if we consider the entire sphere of the moon, it's always half lit. But we're seeing half of the lit half. So we're actually only seeing a quarter of the moon. From the 10th to the 15th, the moon is in a waxing gibbous phase. Waxing because it's still getting more light, and gibbous is the name of that fat lemon shape. The full moon is on the 16th. Notice that during all of those waxing moons, between the 2nd and the 15th, the moon's right side is always lit. After full moon, we start to go back the other way. From the 17th to the 23rd, we have what is called the waning gibbous. It's still a gibbous because it's still that fat lemon shape, but it's now waning, meaning that the amount of light is decreasing. The 24th is called the third quarter moon. Notice we didn't have a second quarter moon. That would have been the full moon. Then from the 25th to the 30th, we have the waning crescents. Notice that all the waning moon phases are lit up on the left. The dorky way to remember that is if it's lit on the right, it's getting bright, going toward the full moon. But if it's lit on the left, it's getting less light. On the 31st, we're back to another new moon. It's important to note that the full moon doesn't always occur on the 16th of each month, or that the 17th to the 23rd aren't always waning, but the path always goes in these orders and takes the same amount of time. Here you can see an image trying to show you two things at once. In the outer circle, it's trying to show you that the moon is always half lit up, whichever side is pointing toward the sun. The phases, though, are caused by the angle at which we are viewing the lit part. We usually only see part of the lit half. Only at full moon do we see the entire lit half of the moon. Your next assignment will walk you through how we see these different shapes, even though the moon is always half lit. Now look at this image. It's showing you the same information as the last image, but this time the sunlight is coming from a different direction. Same picture, but from a different point of view. Notice that the new moon is still between the sun and the earth. Waxing moons are still lit on the right side as we go toward the full moon, and the waning moons are lit on the left as we go back toward the new moon. Anytime you have to draw or visualize moon phases, always start with the new moon that's between the sun and the earth. So the four main shapes are full, when the entire side we see is lit, the crescent, when we only see a thin banana shape, a quarter moon, when we're seeing half of the lit half, and a gibbous, that lemon shape, when we're seeing more than half of the lit portion. Make sure you understand the difference between waxing and waning. Waxing is the 2 weeks after the new moon, as we're going toward full, as the amount of light we see is increasing, and full moon is the middle of the cycle. Then the moon begins waning, and the amount of light we see decreases each day until we get back to the new moon. Now let's practice. What phase is this? Pause the video between each image and see if you can guess the phase before you move on. Hopefully, this one is obvious. Full moon. We see the entire illuminated side. Does this image show us the near or the far side of the moon? I hope this one is obvious too. Have you ever seen the moon looking like this before? Well, not unless you've got a rocket that can take you around to the back side of the moon. This is the far side of the moon. It's much more cratered than the near side we usually see. We only have images of this side from spacecraft that have orbited the moon. We'll talk more about why the front and back sides of the moon look so differently in Unit 2. What about this phase? Notice that it looks like half is lit, which gives you one clue, and that it's lit on the right side. It must be the first quarter, because when the moon is lit on the right, we're in the first part of the cycle going toward the full moon, so this half-lit part is first quarter. How about this one? Banana shape on the right? This is the waxing crescent. It must be waxing again because it's lit on the right. Does this image show us the near or the far side of the moon? Hopefully you can tell that this is the moon looking like it always does. This is the near side. Notice the darker areas with many fewer craters. These are called maria. Maria means seas in Latin. Though they aren't actually seas, that's what early people assumed they were. They're actually old lava flows that have fewer craters because they've been filled in with lava. What about this phase? Lit up on the left this time. And notice carefully how much is lit. It's very close to a third quarter moon, but it's still ever so slightly lit more than halfway. So this is still a waning gibbous. Hopefully you can tell the difference between this one and the last one. This one is exactly halfway. This is the third quarter. Remember, you can tell it's third quarter because it's lit on the left. A first quarter moon would be lit on the right. From which direction does the moon rise? A hint is that the sun and stars also rise from this direction. Everything we see in our sky rises in the east and sets in the west, since Earth rotates from west to east. What about this phase? Lit on the right side, slightly more than half? This is a waxing gibbous. And this one? Tiny skinny banana of light on the left? This is definitely a crescent, specifically a waning crescent, since we're almost back to new moon, lit on the left. What about this one? Be super careful. It looks full, but it isn't. Can you see this tiny bit of shadowiness here? It's not quite fully lit. The dark is on the left, so it's lit on the right, a waxing gibbous. And this one? No, there's nothing wrong with your screen or with the video. This is the new moon. At the new moon, the lit half is turned completely away from the earth, so we can't see anything at all. Those are the phases of the moon. Now, have you ever seen the moon looking like this? It's a waxing crescent, but you can still see that even though it's not fully lit, we can still actually see the other part of the moon. That's called earthshine. The brightly illuminated part of the moon is reflecting light directly from the sun. But here, we can see the other part of the moon, although not well, because light from the sun is reflected off the earth that then reflects onto and partially illuminates the moon. Very cool. The last movement of the moon is called libration. If you watch the PowerPoint in slideshow mode, the video is embedded. The program I'm recording this video in, unfortunately, does not have that capability. I've linked the libration video, though, to the website module just under where you clicked to start this video. Libration is kind of a hula hooping motion that actually allows us to see slightly more of the moon in a month than just half. The moon rotates back and forth slightly as the phases change. It's a wobbly motion similar to the precession that Earth has. You might be wondering why, as the moon moves around the Earth once a month, we don't also get eclipses once a month. The reason why is that the sun, moon, and Earth are rarely perfectly lined up. The moon's orbit is actually slightly tilted compared to the plane of the ecliptic. Most of the time, the moon is slightly above or slightly below the plane of the Earth and the sun. So eclipses are much rarer than full and new moons. But when they happen, they can be very impressive. Notice again how similar those two words are. And that's because they're related. Eclipses happen when the moon's orbit happens to line up with the plane of the ecliptic. Solar eclipses occur when the moon moves between the Earth and the sun, blocking the sun's light from Earth's view. Sol means sun. So solar eclipses are when sunlight is blocked. Lunar eclipses are when the moon passes behind the Earth and into Earth's shadow. Luna means moon. So lunar eclipses are when moonlight is blocked. Solar eclipses always happen during a new moon phase, and lunar eclipses always occur at the full moon phase. But again, they don't happen every month because the moon's orbit is tilted. Here's the geometry of it. In a solar eclipse, the moon blocks the light from the sun entirely for a very small part of Earth, that dark shadow area, which is called the umbra. A much larger part of the Earth gets a partial eclipse and is in part shadow, called the penumbra. Notice the order of the objects here. The moon is between the Earth and the sun. It's important that you know the order of objects for each type of eclipse and what's happening in each situation. This is how a full solar eclipse appears. The moon is in front, but not illuminated from Earth's point of view because the lit half of the moon is pointing back toward the sun. The fuzzy bit of light that you see around the edges is actually part of the atmosphere of the sun called the corona that we normally can't see because the sun itself is too bright. The moon casts a shadow on the Earth. Total solar eclipses are very rare, but partial eclipses, like the one we had in 2017, are much more common. This image shows you an older solar eclipse and how the shadows are actually cast on the Earth as the moon moves relative to the sun and Earth. During a new moon that is not an eclipse, the moon still casts a shadow into space. The shadow just doesn't hit the Earth's surface. Here's a picture taken from the old Mir space station as it orbited the Earth during a solar eclipse. This shows the shadow of the moon created during a solar eclipse. This map shows all the total solar eclipses for a 25-year period. Notice how few they are and what a small part of the Earth's surface they cover. Most areas won't see a total eclipse at all in this time period. Note that the solar eclipses of 2017 and 2024 are visible to part of the United States, but only those directly on the curved paths will experience a total solar eclipse. Areas to the sides of these paths may experience a partial eclipse, though. This shows the view of a partial solar eclipse. Most of the sun is visible, but part is obscured by the moon. This image shows you several photos from the same eclipse, illustrating how the sun's visible portion changes as the moon moves in front. In the center picture, you see what is called an annular eclipse. This occurs when the moon is at apogee, when it's farther away from the Earth, and it doesn't completely block the entire disk of the sun. If the moon had been at perigee, at its near point to the Earth, this would have been a total eclipse. Whether you see a total eclipse or an annular eclipse just depends on the distance of the moon from the Earth, whether it's at perigee or apogee. When the full solar disk is hidden by the moon, solar telescopes can also see solar storms like this prominence leaping off the sun's surface. Here is another picture of an annular eclipse. If the moon had been closer to Earth, it would have been a total eclipse. Here, though, we see a portion of the solar disk making a ring shape called an annulus. Now let's look at lunar eclipses. Here, the moon is on the back side of the Earth as seen from the sun. Sunlight shines on one side of Earth, but then Earth casts a shadow into space. As the moon passes behind the Earth, it falls into the shadow. Lunar eclipses occur at the full moon, but you can see that as the moon passes into the shadow, part of the light is blocked. Notice that the total lunar eclipse, though, is not black, but red. This is sometimes called the blood moon. Even though the moon is in Earth's shadow, the moon still gets a little bit of light that is bent through the Earth's atmosphere and onto the moon, which causes the reddish color. These lunar eclipses are more common than solar eclipses, since the Earth casts a much bigger shadow into space than the moon does. Here's a diagram just illustrating the differences between the two types. Make sure you know the orientation of the three objects during each eclipse and how the light is being blocked. From the Earth's point of view, a solar eclipse looks dark because what we're seeing is the new moon. A lunar eclipse looks reddish from the light being bent through Earth's atmosphere. Finally, our last topic of this lecture is tides. Tides are caused by the pull of the moon's and the sun's gravity on Earth. The moon is the main cause of tides, but the sun has an effect as well. Tides occur on the side of the Earth pointing towards the moon and on the back side. In this diagram, high tides would occur here and here. Low tides would be happening for people here and here. If you watch the PowerPoint in slideshow mode, this diagram and the one on the next page are animated so you can see how the water rises and falls with the passing moon. The reason is that the moon's gravity causes the water to collect in the direction of the moon. Earth's rotation causes a similar bulge of water on the back side because of Earth's rotation. So here, two areas of the Earth have much more water than they should have, high tide, while the other two sides of Earth have less water than they should, low tide. These are the normal daily tides that occur roughly twice per day. Tides are slightly later each day due to the moon having to catch up with Earth's new position as it travels around the sun. There are also two other special types of tides. Regular high tides and low tides are caused by the moon's gravity, as seen in the blue areas. But the sun also has an effect on the tides, represented by the red areas. The sun's effect isn't as great since the sun is so much farther away than the moon is. A neap tide is when tides are smaller than normal. The sun, the earth, and the moon are at right angles to one another. Here, the moon is pulling the water in one way, and the sun is pulling the water in the opposite way. They partially cancel out, making the tides lower than they usually are. The opposite situation is called a spring tide. Here, the sun, the earth, and the moon are all lined up and are working together to make larger than normal tides. And one last note, you've probably heard someone call another person a lunatic. My old cat Stinky was a lunatic. This word comes from back in history when people thought the moon affected people's behavior. It doesn't, but the word still exists. Finally, a joke. Take a look at the 17th. Stay in, stay in, stay in, then full moon, go out. Werewolf planner. Kind of funny.